Last time we did the basics of probability, and you saw the proof of inclusion exclusion principle, which is probability of union, and then you saw this very nice classical example of counting derangements, or the probability that all the letters will be wrongly delivered. So today we will start this one formalization that we postponed, which is what is the meaning of probability in an infinite space. Okay, so let's start that. So probability for infinite omega, infinite sample space. So the thing is, here we may not be able to do a sum of probabilities, because sum may not always be defined if it is an infinite sum of infinitely many things, right? Then you get into convergence issues. So we may not be able to go one element at a time, and the reason is this sigma p omega, this way of doing things may not work, especially when you are doing it for a subset, right? This may be undefined. That's the problem. So instead what we will do is we will work at the level of subsets. We will define probability directly for subsets and not for elements. So instead we work with subsets, which is events, directly. So how do you do that? So for that we have to define what kind of subsets are allowed. So that is sigma algebra. So collection E of events or subsets is called a sigma algebra. If it has nice closure properties. So since we are not working with elements but subsets, we still want the subsets to contain some information about the elements within, right? So in particular you want to take intersection, union, complement, those kind of things, and then the probability map or operator should extend suitably. So you want full space to be in E, omega should be in E. You want closed under complement, which means what is closure? Closure simply means that if A is in E, then A complement should also be in E. That's what closure means. And finally, E should be closed under union. But remember that now you are talking about infinitely many subsets, right? So what is union? How many subsets could you take the union of? So we will want to work with good kinds of infinity, which is countably many subsets. So countable union. So what is this word countable? Countable simply means that the number of subsets that you are taking union of, that number or that index set should be in bijection with or should not be bigger than let us say numbers, natural numbers, okay, or integers. So, it is like 1, 2, 3, 4. So, first subset, second subset, third subset and so on. That kind of union you are allowed, but not something uh, which is bigger than this, which is not in bijection with 1, 2, 3, 4 natural numbers. So, let me mention that separately. So, in case you do not know, a countable infinite set is always in bijection with natural numbers and also in fact integers and also with rationals. Okay, so that you can take also as the definition of countably infinite. It is like natural numbers, integers or rationals, but not with reals. Okay, so reals is not in bijection with natural numbers. Okay, reals is something far more. It is actually like subsets of natural numbers. But we will not go too deep into that. So, it suffices to say that you are allowed to take union where the index set is natural numbers. Okay, that is the intuitive thing. So, union of subsets natural numbers is allowed inside E. Okay, that's it. So, that is what is meant. So, such a collection is called a sigma algebra. And now, once you have a sigma algebra, you can define the probability map. So, next thing is probability distribution function P is a map from this sigma algebra to the real line 0 to 1, real line, in fact the segment 0 to 1. Okay, obviously, which satisfies. So, to define probability, remember. So, what it should satisfy is that probability of the full sample space should be 1, and since you want the probability to also extend to other subsets, what you would like is it should respect somehow the sigma algebra operations, in particular union. So, for all AB that are disjoint, probability of union is the sum. Okay, and this is enough to extend P to the whole of sigma algebra. Okay, you define it over disjoint, and then this will help you together with the countable union to extend to any subset, because E is a sigma algebra. So, that I leave as an exercise. Okay, this is the meaning of probability over infinite spaces. So, above defines probability of AI for any index set that is countable. And second is the same thing for intersection. So, defines for union, countable intersection, and other kinds of union also. For example, you can recover the union formula by subtracting intersection. Okay, so all these things could be reduced. So, these things should be intuitively clear. What we have done is just given you the formal definition of probability distribution over infinite sample space. The idea being move from elements to subsets. Do not talk about probability of an element. Okay, that in fact may not even be defined, but what is defined is probability of a subset of an event. So, what are the examples of sigma algebra? These are the immediate examples. So, if you just take empty set and everything, that is a sigma algebra, it is a trivial kind of a sigma algebra. Okay. It is closed under, it has omega, it is closed under countable union and complement. Those were the three conditions. Then you can extend this, make it slightly bigger by adding a subset, then you have to add its complement. So, this you can do for any subset. Right. Now, remember that this probability may not be half, right, just A and its complement being the subsets in your sigma algebra does not mean that they are equiprobable, right. It may also be 1/3, 2/3 probability. So, that will depend on the problem definition, how you define P. And there is another trivial example which is just all subsets. You can also take all subsets of omega. So, which is E such that A is a subset of omega, all of them, and which is also kind of functions Boolean valued. Right. So, you can look at the events as either subsets of the sample space, or you can think of them as 0, 1 valued functions, but then the sample space will be that of functions as well. But this I should, yeah, that is kind of a diversion. The important definition is the first one. Okay. Another example, slightly more interesting example. Infinite sample space example is suppose you pick a random number, so physically you are picking a random number x between 0, 1, and you are interested in the probability or chance that it is smaller than 0.5. Okay, you are interested in this probability. So, what is the probability distribution function for this with the sample space? So, the way you can model it is define your sigma algebra to be empty set, everything which is 0 to 1, and the subset of interest which is 0 to 0.5. and the complement of it. Okay, so let's call this A, and then this is A complement. So in the sigma algebra, there are only these 4 elements: everything, nothing, and subset of interest, event of interest, and its complement. These 4 things, right? And intuitively, the probability of A should be attached half, right? Because its length is half of the sample space. So intuitively, you define like that. So intuitive P is which sets probability of A to be half, right? But you could have given this A any probability, that also will be a valid probability map. For example, you can assign probability of A to be 2/3 or 1/3, and then the other one will be 2/3. Okay, that is also a valid probability map. But the intuitive one is this, and this is called uniform distribution. Right. So the uniform probability distribution map or function is the one that gives an interval probability value difference of the endpoints, the length of the interval, right. So we can in fact then define E to be something like this. So it is also consistent with an E where you have interval A comma B for every possible AB, and also you have to put obviously the empty set, empty interval with probability of the interval, the difference. Okay, so this is how you can make sense of picking a random number x in the interval 0 to 1 and saying that the probability it is at most 0.5 is half, 50% chance, right. So you make sense of it by saying that okay, my sigma algebra is this and my probability distribution function is this, consistent with uniform distribution. So I can mathematically say that the probability is half for getting 0 to 0.5. Okay, so an intuitive thing can be explained mathematically like this. In fact, this even models reality. So in the same spirit, we can go back and explain the random chord example that we did last week. So the prior example of random chord dE in a unit circle, right. So recall that it was like picture was like this. You have an equilateral triangle centered at O, and the circumscribing circle is also drawn. We have assumed the radius to be 1, and hence the side is square root 3. Right, using trigonometry you can show that. And the random chord is this dE with center F. Right. So what is the chance? Question was what is the chance that this random dE chord has length more than square root 3? So the probability that the chord length is at least square root 3. What is this? And in fact, since this is an infinite sample space, how do we make sense of this? That there are infinitely many possibilities of picking the chord, even picking the point D. So we got 3 different answers by using 3 different experiments. So I'll just quickly explain to you the formalization of each of those 3. So the first was you model your sample space as take your D to be A and E to be random on the circumference. So the border of the circle squared. Okay, so this is the boundary of the circle. So on the boundary, you were thinking in terms of picking a random E, taking D to be D could have been anything. So without loss of generality, we fixed it to be A, and then E is what is being picked from the boundary of the circle. So these are all possible such chords, and so this is the sample space, and the relevant sigma algebra that you have to define contains empty set, sample space, and those chords which are long. Right, those are the favorable chords. So let's call this set A1 and A1 complement. And P1 you take to be uniform on omega 1. Right. So uniform on omega 1 means that the only thing that is changing is E. So you take it to be everywhere with the same chance, whatever that means. Mathematically, you will just define P1 to be on an arc. What is the chance of point being on an arc? So length of the arc over 2 pi, the circumference of the circle, right? That will be the probability. And so this is enough to give you the probability of A1, which I think you got 1/3. Okay, second way to model this mathematically and rigorously is to take omega 2 to be this collection of F. So F on the circle. Okay, so the circle is not just boundary but everything. So this is area of the circle. Okay, so that, and then in this case the sigma algebra that you will pick is the empty set, everything, points F such that DE is long. So let's call this A2 and its complement. Right, and then the probability map will be uniform on omega 2. So uniform on omega 2 means that this point F can be anywhere in the area of the circle. So if you restrict it to some zone, then the area of that zone over pi, which is the area of the circle, is the probability. That is what is meant. So this I think gave you probability 1/4. Probability of A2 came out to be 1/4. Again, it's completely correct in this formalism. So P1 and P2 are different probability distributions. Okay, that was the point. So both of them hold true. And then the third one was looking at the length of OF. That is the third kind of formalism. So, you can take sample space to be the segment OF, center of the circle to center of the chord, F everywhere in the circle. And the sigma algebra you can define as empty set, sample space, OF with DE long, let us call this A3 and its complement, right, similar to the definition before. And of course, P3 is now uniform on omega 3 with respect to length. So, the segment you can take all lengths with kind of equal chance and also all directions with equal chance, right. So, it ultimately boils down to the length, which favorite was the favorable length was half or less, right. So, you got probability half there. So, 1/3, 1/4 and 1/2, these were the three possibilities. They are all correct, depends on which probability distribution you are looking at, P1, P2 or P3. Thus, the probability respectively are all correct. And why are they all correct for the same event? Well, because it is not really the same event, it is happening in different probability distributions. So, omega p is critical. So, definition of omega p is critical. That is the reason. That is all you need to define probability over discrete space or over continuous space. So, next what we will do is a very important, you can say, operator on events, or you can say type of probability, which is called conditional probability. So, here the question you ask is how does extra knowledge help you? Extra knowledge B affect the probability of an event A. Okay, so the question you are asking is what is the probability of event A? And in a different scenario, if you had prior information about some other event B, what is the probability of A? Okay. So, with the knowledge and without the knowledge of B, how does the probability of A change? Right. So, this relative probability or conditional probability is a very natural question and it has huge implications. In fact, as you will see later, huge practical implications as well. So, this is a question different from what we have studied till now. So, this question is different from complement, union, intersection, minus etc. that you saw. right? It's a different kind of operation that we are doing with A and B. In all the other cases, B was not certain, right? It was always either B complement or A union B or A intersection B or A minus B. Uh, but now we are saying that certainly B has happened and then A is yet to happen. But this is still somehow related to relates somewhat to intersection. Why is that? Well, just consider the following picture. So in this picture, this is the intersection. So B has already happened. And what is the chance that A will happen? So B happening means that you are considering the shaded part. Right. So in this yellow shaded part, what is the chance of, or what is the fraction of this orange shaded part, right? This is what you are interested in. So it is somehow related to intersection, but it's not intersection as a whole in the whole space, sample space, but relative to B, right? And that can change everything, because then the question arises, how big is B compared to omega? If B is very small, then the conditional probability should be very small. Well, it can be, yeah, it isn't clear. Even if B is very small or B is very large, still you have to look at the intersection relatively. So it really depends on, so without B, the analysis was looking at A versus A complement, right? With B it will be different.